All right, so let's start with chemical energetics. What does it deal with? So this topic deals with the feasibility of a reaction. So it deals with the feasibility of a reaction, whether the reaction is feasible or not, based on energy. Now, there are two types of reactions. We have exothermic reactions and we have endothermic reactions. So let's see the energy profile diagram for an exothermic reaction and an endothermic reaction. So you have two types. You have exothermic reactions and you have endothermic reactions. Now, if we see the energy profile diagram for an exothermic reaction, in an exothermic reaction, the reactants always have more energy compared to the products. And in the endothermic reaction, the reverse happens. So let's see the exothermic reaction energy profile diagram. Now, on your y-axis, let's say we have energy, and on the x-axis, we have the reaction progress. So you have reaction progress on the x-axis, energy on the y-axis. In exothermic reaction, the reactants always have more energy. Is why sometimes we also call exothermic reactions what? Spontaneous. Because the reactants already have a lot of energy. They can mix, react, and give you the product. They don't require a lot of external or activation energy. So reactants have high energy, products have low energy. This right here is your exothermic reaction, where reactants have high energy, products have low energy, and then we connect the two. Therefore, this right here, this bump right here, this becomes your activation energy, right? And from your reactant to the product, right here, this arrow corresponds to the delta H of the reaction, where we say that delta H of the reaction is energy of products minus energy of reactants. Yes? Now, you can see right here that, let me just take fake values. So this, let's say, is 8. This, let's say, is 2, the energy. So if you do energy of product minus reactant, it will be 2 minus 8. And you see this comes out to be a negative value. So exothermic reactions, they always have a delta H, which is negative. So they always have a negative delta H. Yes. In exothermic reactions, the reactants have more energy than the products. In exothermic reactions, the activation energy is low. As you can see, do you see this is the activation energy required? Now, what is the activation energy? It is the minimum energy required to initiate a reaction. Yes, and that is low. And we can say, therefore, exothermic reactions are spontaneous reactions. Why do we call them spontaneous reactions? Because the reactants have high energy. They can react and give you the product. So these are sometimes referred to as spontaneous reactions. They can happen on their own without external help, right? Now, in exothermic reactions, energy is always released in the surroundings. So exothermic reactions, they increase the temperature of the reaction mixture. So you have release of energy. So energy is released in the form of heat. Therefore, there is increase in temperature, right? And the delta H we have already seen will be less than 0 or negative. Clear? So this right here are some properties or some properties of the energy profile diagram for an exothermic reaction. Clear? Now let's see endothermic. So let's see the endothermic profile. Now again, on the y-axis, you have your energy. On the x-axis, you have reaction progress. Now, in your exothermic reactions, the reactants had higher energy, products had lower energy. In your endothermic reaction, the reactants have low energy, products have high energy. So these are your reactants, these are your products, and then you connect the two like this. So this entire thing right here becomes the activation energy. So this entire thing is your activation energy. And you see, you require a lot of activation energy. And is why these reactions are non-spontaneous. because they will require a lot of energy. And from reactant to your product, this right here is your delta H of the reaction. Clear? Now we know that delta H of the reaction is energy of products minus energy of reactants. Now let me take values for the reactant and the product. So let's take this to be 2. Let's take this to be 8. Product is 8, reactant is 2. This will come out to be plus 6. So do you see that for endothermic reactions, the delta H is greater than 0, or it would be what? Positive. Yes? In endothermic reactions, there is high activation energy, right? And why is that? Because reactants have low energy compared to the products. So reactants have low energy compared to the products, and is why you have high activation energy. In endothermic reactions, energy is absorbed. Do you see a lot of activation energy is required? So energy is absorbed from the surroundings. So in these reactions, energy is absorbed. And since the energy is absorbed, we can say the temperature would decrease, right? So the temperature decreases for endothermic reactions. And in exothermic, the reverse happens, temperature increases, and delta H is less than 0 or negative. Reactants have more energy than the products. Clear? Now, we say that delta H can be calculated by energy of products minus energy of reactants. That's what we say. Now, let's first see what is the delta H here. The delta HR over here is the enthalpy change of reaction. Enthalpy is just a fancy word for energy. Yes? So energy change of the reaction or enthalpy change of the reaction is the same thing. So delta HR stands for enthalpy change of reaction. What is EA? EA stands for activation energy. And we know what is activation energy? It is the minimum energy required to initiate or start a reaction. So what is activation energy? This is the minimum energy required to initiate a reaction. Now, I told you that we can find delta H how? By energy of products minus energy of reactants. Let me take a reaction. Let me take an example of a reaction where you have calcium carbonate decomposes into calcium oxide and carbon dioxide. If I ask you to calculate the delta H for this, what would you say? It would be delta HR is equals to energy of products. What are your products? Calcium oxide and carbon dioxide. So can I say it would be energy of calcium oxide plus energy of carbon dioxide minus the energy of the reactant, which is calcium carbonate. Yes? But the thing is that we can't really find the exact value for energy of a reactant or a product. So we can't get what I have written here on the y-axis, this energy. You can never really get the exact value for the energy of reactants and products. You can't do that. So what will be on the y-axis then, if not energy? And why not energy? Because exact energies cannot be measured for reactants and products. So you can't use energy, is why we use enthalpy change of formation instead. Now, what is that? Let's see. So we know that delta HR is equals to energy of products minus energy of reactants cannot work because you can't get exact energies. Yeah. So now what will we use instead? We will use delta HR equals to enthalpy change of formation of products minus enthalpy change of formation of reactants. So we use this instead. In fact, over here, I have labeled energy on the y-axis, which is not really true. It would be what? Enthalpy change of formation on the y-axis and reaction progress on the x-axis. And why not energy? because we can't get the exact values for energy. Now, what is this enthalpy change of formation? So let me just first say this delta HF with a sign on the top, this phi, this means standard conditions. And I'll just explain this to you. So this right here is called the standard enthalpy change of formation. So you can't use energy, is why you use what? Enthalpy change of formation of product minus enthalpy change of formation of the reactant. Clear? Now, what is this enthalpy change of formation? So let's take an example now. So if we have a reaction where we have strontium carbonate decomposing into strontium oxide plus carbon dioxide, and we have to find the delta HR, what will we say? It will be formation of SRO or strontium oxide plus formation of carbon dioxide minus formation of the reactant, which is strontium carbonate. Clear? So it will be formation of products minus formation of reactants. Clear? Now, let's see, what do you mean by enthalpy change of formation? So let's define standard enthalpy change of formation. So let's see what this is. This is represented as delta H. Why delta H? Because delta means change in energy. Energy is represented by H. Delta H means change in energy. Because it's energy of formation is why we put an F. And because it is under standard conditions is why I put this sign right here, which is phi, which represents standard conditions. So this would be what? Enthalpy change of formation, and because the conditions are standard, hence the phi. Now, what do you mean by standard conditions? For all the energy changes that we will be studying in energetics, we will be calculating all the values under standard conditions. And those standard conditions are 25 degrees Celsius temperature and 1 atm pressure. That is your standard condition. So all values that we will be calculating in energetics, they will all be under standard conditions. And what are your standard conditions? So all reactions in energetics that we'll be studying would be under standard conditions, which are 25 degrees Celsius temperature and 1 atm pressure. And how do we represent the standard conditions? By this sign, this phi sign represents standard conditions. So you have delta HF. Let's see, this delta H means change in energy or enthalpy. F means formation. And this phi sign implies standard conditions. Is this clear? Yeah. And what are the standard conditions? 25 degrees Celsius temperature, 1 atm pressure. Now let's see, how will we define standard enthalpy change of formation? So delta HF is defined as the energy change. Energy change means whenever we say the word change, energy change, that means this could be exothermic or endothermic. If I say it is the energy change when, or if I say it is the heat absorbed, or if I say it is the heat or the energy released, if I say absorbed, that means the energy change is endothermic. If I say released, that implies it would be exothermic. But if we say the energy change, that means it can be exothermic or endothermic. So it is the energy change that occurs when 1 mole of a product is formed from its constituent elements. Let me define it first, then I'll explain it. It's pretty simple. So it is when 1 mole of product is formed from its constituent elements in their standard state under standard conditions. We call this what? Enthalpy change of formation. So what is enthalpy change of formation? When 1 mole of anything is formed from its constituent elements in their standard state under standard conditions. Now let me explain to you. Before I move on to explaining what enthalpy change of formation is, can I say that let's take decomposition of calcium carbonate. So over here on the y-axis, we will have what? Enthalpy change of formation. And right here, we will have what? Reaction progress. So I'm taking this reaction right here, which is calcium carbonate decomposing into calcium oxide plus carbon dioxide. Decomposition is always endothermic because in decomposition, you have to break the bonds. And for that, you have to give energy. So decomposition is always endothermic. So can I say, since this is endothermic, the reactant will have less energy, product will have more energy. So this is the reactant and this is your product. And this right here would be your activation energy. The entire thing right here would be your activation energy. And this right here would be the delta HR. And can I say the delta HR would be formation of calcium oxide plus formation of carbon dioxide minus the formation of calcium carbonate. Clear? Formation of product minus formation of reactant. Now let's get on to explaining what enthalpy change of formation is. I've already defined it for you. Let's see. Now what is it? It is the energy change which occurs when 1 mole of anything is formed from its constituent elements in their standard state under standard conditions. So let's see. And what are your standard conditions, by the way? 25 degrees Celsius and 1 ATM. So let's see now. Let's take the example of NaCl. Now, what is enthalpy change of formation? It is formation of 1 mole of something. So how much should NaCl be? 1 mole. So it is a formation of 1 mole of anything from its constituent elements. What are the elements in NaCl? Sodium and chlorine. And they should be in their standard state. What is the standard state of sodium? Sodium, solid. And chlorine naturally exists as what? Cl2 gas. Do you see? 1 mole of compound or 1 mole of anything being formed from its constituent elements in their standard state under standard conditions, which are 25 degrees Celsius and 1 atm pressure. That is called what? Enthalpy change of formation. Now you have to balance this. So when you balance this, you cannot make this 2. Why? Because for formation, how many moles of product should be formed? 1 mole. So you can't, for the Cl, you can't balance it by putting a 2 in front of NaCl. This would therefore be half. Clear? And we will call this what? Enthalpy change of formation of NaCl. Clear? Now let's see. Let's write down the equations for enthalpy change of formation of MgCl2, AlCl3. Let's write it down. Magnesium chloride, how much should it be formed? 1 mole. From its constituent elements, what are the elements in MgCl2? Magnesium and chlorine. What is the standard state of magnesium? Magnesium, solid. What about chlorine? Cl2 gas. This right here becomes your equation for delta HF of MgCl2. Is this clear? Let's see AlCl3. How much AlCl3 should you make? 1 mole. From its constituent elements, which are aluminum solid and chlorine gas. Now, how many chlorine do we have on the product side? 3. How many do we have on the reactant side? 2. So what will be put here? 3/2. Clear? And it is balanced. Does this make sense? So this right here is enthalpy change of formation, where 1 mole of anything is formed from its constituent elements in their standard state under standard conditions. Clear? Can you guys try to write the equations for formation of C6H12O6? Write it for H2SO4, for C3H8, K2Cr2O7, CH3CO2H, C2H5OH. Very quickly, write down the enthalpy change of formation for all of these. So let's see now the equations for enthalpy change of formation of glucose. So you have C6H12O6. What are the constituent elements? Carbon. So carbon naturally exists as carbon solid. Then you have hydrogen, which is the hydrogen gas. Oxygen, which is O2 gas. And this must be 1 mole. You have 6 carbons here, you'll put a 6 here. 12 hydrogens here, we'll put a 6 here. 6 oxygens here, we'll put a 3 here. This right here becomes enthalpy change of formation of glucose. H2SO4. So this is 1 mole made up of its constituent elements. What are the constituent elements? Hydrogen naturally exists as H2 gas, plus sulfur naturally exists as sulfur solid. Actually, sulfur, you'll do this in period 3. Sulfur exists as S8, but over here you can just write S, that is fine. Right? So this is sulfur solid. And then we have oxygen, which is O2 gas. Hydrogen's balance, sulfur's balance, oxygen would be what? 2. If you were using S8, then you would have had to put what? 1 upon 8 over here. Because sulfur naturally is not S. Sulfur naturally is what? S8. We will do this when we do period 3. C3H8. How many moles should be formed of C3H8? 1. Made up of what? Carbon, solid, hydrogen, gas. 3 carbons here, put a 3 here. 4 hydrogen here, that will give you 8. Clear? K2Cr2O7. So how much should we make? 1 mole. Potassium naturally exists as K, solid. Chromium is also a transition metal, will exist as Cr, solid. And oxygen will exist as O2 gas. Yeah? Now let's balance it. So that's K2, so we'll put a K2 here. Cr2, we'll put a 2 here. O7, so we will put a 7 over 2 here. This right here becomes formation of K2Cr2O7. CH3CO2H, how much should we form? 1 mole. Ethanoic acid. It's made of what? Carbon, which is solid, hydrogen, which is gas, and oxygen, which is also gas. How many carbons do we have? 2. So we'll put a 2 here. How many hydrogens do you have? 4. So you'll put a 2 here. How many oxygens do we have? 2. It is already balanced. C2H5OH. So let's see, 1 mole should be formed from carbon, solid, hydrogen, gas, and oxygen, gas. Now carbon, 2 moles, so we'll put a 2 here. 6 hydrogen, so we'll put a 3 here. And 2 oxygens, so right here we will put a half so that we have 1 oxygen on both sides. Is this clear? These are all the equations for enthalpy changes of formation. Now you see, it is the energy change where 1 mole of anything is formed from its constituent elements under standard conditions, right? In their standard state. Now let's see the SI unit for enthalpy change of formation. So this is energy change. Therefore, the energy change is in kilojoules. And this is the energy change, can I say per mole? Because it is for 1 mole of anything that is formed. So therefore, the SI units would be kilojoules per mole. Clear? Now I told you that we could use delta H formation to find the delta H of reaction. And you've seen that we can find delta H other ways as well. Remember in bonding we did delta H is equals to bonds broken minus bonds formed. You could use bond energies. You can also use delta HF. You can also use something else which we will do next, which is enthalpy change of combustion. So you can find So we can find delta H of the reaction by multiple ways. One, which you've already done, bond energies. And how do we use bond energies? Delta H is equals to bonds broken minus bonds formed. And bonds broken were always of the reactant. Bonds formed were always of the product. This is already covered in bonding. The other way is using enthalpy change of formation. So you can use enthalpy change of formation to find the delta H. And let's see how. So delta H can be found using enthalpy change of formation as enthalpy change of formation of products minus enthalpy change of formation of reactants. That's how we can find delta H. Clear? Using enthalpy change of formation. Now let's see. Let's take an example. A plus B giving C plus D. Using enthalpy change of formation, how will we find the delta H? Can I say delta H of the reaction will be equal to formation of C plus formation of D. These are the products minus formation of A plus formation of B. Do you see that? Formation of products minus formation of reactants. Let's take another example. So if you have C2 plus D2 giving 2CD, let's find the delta H using formation. So what will we do? Delta H R is equals to formation of product minus formation of reactant. What is your product? CD. And how many moles of CD do we have? 2 moles. So what will you do? It would be formation of CD times 2. So this is your product minus formation of reactant. So this would be formation of C2 plus formation of D2. Is this clear? Is this clear? Let's take another example. If you have 2W, 2Y giving 2WY. So what will be your delta H using formation? So can I say, in this case, delta H of reaction would be formation of what? WY times 2 minus formation of W times 2 plus formation of Y times 2. Is this clear? Because delta H of formation is per mole. Remember I told you the units were also what? Kilojoules per mole. But if you have more than 1 mole, then you'll have to multiply it by that number. Understood? Let's see another example. If you have N2 plus 3H2 giving 2NH3. So if you want to find the delta H using formation, what will we say? Delta H of the reaction is equal to formation of ammonia times 2 minus formation of nitrogen plus formation of hydrogen times 3. Is this clear? Is this clear? Understood? Now, if I tell you, write down the formation of carbon. How will you write down the formation of carbon? Write down formation of carbon. What will you write? Carbon, 1 mole being formed from its constituent element, which is also carbon solid. Do you see the reactant and product is the same? Is there going to be any energy change? Because reactant and product is the Same. If I ask you to write down the formation of nitrogen, how will you write it down? You will say nitrogen, 1 mole being formed from nitrogen. Is there any change? No. If I ask you to write down the formation of sodium, you will say sodium from sodium. Write down formation of oxygen. What will you say? Oxygen forming oxygen. What do you see here? What have I listed? All of these are elements. And when you have to write down formation of elements, there is absolutely no change in the reaction because elements naturally exist in that form. I will not have to make sodium because what will I make sodium from? Sodium. And sodium exists simply as sodium. So you don't have to make it from anything simpler. You understand that? And is why you see if I say write down formation of chlorine, that will be chlorine being formed from chlorine. There is no energy change. Is why can I say enthalpy change of formation for elements in their standard form would be what? 0. So if anywhere you see an element in its standard form, it would be what? Formation would be 0. If I say make down chlorine, make liquid, now that's different because chlorine naturally would be what? Gas, and then it's becoming liquid, so that's different. Now this would not be 0. But if you are making elements in their standard form or in their pure elemental form, that would be what? Formation for that would be 0. So can I say that enthalpy change of formation for elements in their pure form would be what? In their pure form is 0. For example, carbon solid making carbon solid, no change, 0. For example, nitrogen gas making nitrogen gas, no change, 0. Because for all elements, they naturally exist in their pure form, and to make that, you will require no energy because that's how they naturally exist. So their enthalpy change of formation would be what? 0. All right, and that will not even be given to you. All right, so if sometimes you'll be doing the question and you'll see oxygen and the formation for that is not given. So you don't have to freak out or be like, where will I find this from? Because formation for oxygen would be what? 0 is why they haven't given you. Because any element in its pure elemental form, all right, would be what? 0. Clear? So what are the, I'm just going to list down a few. So let's see the elements in their pure form. So let's see elements in their pure form. What is the pure form of carbon? What is chlorine? Gas. What is fluorine? Gas. What is bromine? Liquid. Naturally, bromine is liquid. Iodine naturally is solid. Sodium, solid. Magnesium, solid. Calcium, solid. Nitrogen, gas. Hydrogen, gas. These are the ones which you will come across most often. And you should know that all of these, their enthalpy change of formation would be what? 0. Because you don't require energy to make these because this is their simplest form. This is how they naturally exist. Clear? Any questions? So for all of these, enthalpy change of formation would be 0. Understood? Now let's see a question. Let's apply all of this knowledge to a question. All right. So let's see. If I tell you that this is your equation 3FeO plus 2 moles of aluminum solid, giving you Al2O3 plus 3Fe solid. If I ask you to calculate the delta H, provided that, so calculate delta H of the reaction, given that the formation of Al2O3 is minus 1676 kilojoules per mole, and given that formation of FeO is minus 266 kilojoules per mole. First thing, how will we calculate delta H using formation? Delta H is equals to formation of products minus formation of reactants. So you will say delta HR is equals to formation of products minus formation of reactants. Now, if you see in your products, what do you have? Aluminum oxide and iron solid. You've been given the formation of aluminum oxide. Have you been given the formation of iron? No. Why? Because it would be 0, because it is in its elemental form. So you will not regard this, right? This will not be part of your equation. Why? Because we don't use this, because this would be 0. What about aluminum? Aluminum is also in its elemental form. So this would also be 0. So what will you do? What is your product then? Just Al2O3. The value for which is what? Minus 1676. Minus. In the reactant, you have aluminum, but the value for this is what? 0 is why you see they haven't even given it to you. And then you have FeO, the value for which is minus 266. What will I write? Minus 266 times 3. Very good. Why? Because it is 3 moles. And you know enthalpy change of formation is per mole, or based on 1 mole being formed. Is this clear? Do you guys understand this? And this is how you get your delta H, which comes out to be how much? Minus 878 kilojoules per mole. Understood? Do you all get it? Yes? Any questions?